Hi, and welcome to these new videos. As you may have noticed, the location has changed. This is because I just recently moved to Philadelphia, where I will stay for the next 6 months for an internship, but this video is not about this topic. This video is to present you our last accepted paper, a paper we are going to present at ICASSP this year. The venue is in Rhodes, Greece, and the name of our paper is pretty long, so I need to read it. Is Exploiting Prnu and Linear Patterns in Forensic Camera Attribution under Complex Lens Distortion Correction. A work co-authored by Fernando Perez Gonzalez and me. In this paper, we address the problems of source attribution of radially corrected images, specifically focusing on radially corrected images by the in-camera software of compact cameras, which are more simple and tend to rely on simple barrel or pinkish distortions, and the more complex one applied out camera by common editing programs such as Adobe Lightroom, Photoshop, GIMP, and PT Lens, which, relying on a much powerful hardware, can apply adaptive and variable radial corrections. But why radial correction is a problem for source attribution? Camera source attribution is mostly accomplished by a scanned and invisible residual introduced by the sensor of our device every time a light source falls onto it, called photoresponse non-uniformity, or PRNU. This one can be extracted from any images or video taken with a certain device by applying a wavelet denoiser followed by a linear filter in the FT domain and subtracting the zero mean by rows and columns. After that, we can compare this PRNU with another PRNU extracted from another images in terms of peak of correlation energy, or PC, to check whether they were taken with the same device. However, the PRNU is also very sensible to any kind of spatial transformation and shifts, like those occurring, for instance, during radial corrections, which dramatically reduce its consistency and requiring to invert the spatial transformation before measuring the PCE. For these reasons, in the last decades, a few methods have been developed in order to recover the PRNU consistency by inverting the radial correction applied to the image and, of course, to its PRNU. Precisely, the two most relevant work are sensor fingerprint-based identification of images corrected for lens distortion and estimation of lens distortion correction from single images, both co-authored by Miroslav Goljan and Jessica Fridrich. In their first paper, the author used a combination of a grid and a golden search in order to estimate the radial correction parameters of these models and invert the radial correction applied to the PRNU. This method demonstrates on a large and diverse dataset composed by many images taken with compact camera to reliably accomplish its task. However, being able to invert only simple barrier or pinkish distortion, and due to the downsamplings of 2x2 used to reduce its computational complexity, it really struggled with images radial corrected out camera, as we will show later, and with low resolution images. In order to consider a much more complex radial correction models, the same author in their next paper tried to estimate two separate and independent radial correction parameters of these models by exploiting the so-called linear pattern. With respect to the previous solutions, the authors decided to use this time the linear pattern energy as maximization functions in order to estimate alpha 1 during a grid search. Only after that, alpha 1 is refined and alpha 2 is going to be estimated using the another methods. Finally, alpha 1 and alpha 2 are validated by computing a second-order polynomial that is then subtracted to the maximum energy obtained for alpha 1 and alpha 2 and compared with a threshold. Indeed, the methods always find a linear pattern energy maxima for alpha 1 and alpha 2 even if no radial correction was even applied to the images. And this has to be validated in order to avoid false positives. The main advantage of this method with respect to the previous one is being able to invert much more complex radial corrections, estimating two independent parameters without requiring, as in the previous case, a PRNU ground truth to do so. Nevertheless, while performing slightly better under this condition, it can only invert barrel-like distortion due to its implementation, while still producing many false positives and so failing during the validation process, not exploiting for further check the PCE. Nonetheless, after evaluating these two methods on our dataset, a dataset composed by 3,645 images, of which 2,037 were downloaded from Flickr and taken with compact camera, so that they were radial corrected in camera, and the remaining one instead were taken with DSLR camera, the Canon 1200D, and then radial corrected out camera with Lightroom, Photoshop, GIMP and PT Lens, we noticed that the two methods of Goljan and Fridrich were kind of complementary, performing differently on different type of radial correction. For this reason, we first thought to simply combine these two methods with a simple OR or max rule that we are going to explain right now, and then try to propose something more sophisticated and computationally more efficient. The max rule consists in running the two state-of-the-art methods both in parallel or sequence, and then taking the maximum between their PCE values and comparing it with the thresholds in order to perform camera attribution. On the other hand, the OR rule is much simpler, consisting in proclaiming a match if either one of the two methods return a PCE value larger than their respective threshold. Although this solution provides some improvements, they are not as efficient and they are not really focusing on the strong point of each of the two methods of the state-of-the-art. For this reason, we propose a PCE-guided coarse parameter search plus linear pattern energy-based refinement method. This latter estimates two independent radial correction parameters by first finding alpha 1 using the PCE-guided grid search of sensor fingerprint-based identification of images corrected for lens distortions without this early stopping condition. Thus, we validate alpha 1 exploiting the nature of the PCE and checking that its PCE values correspond to the global maximum by comparing it with the average of two PCEs retrieved away from alpha 1. And if alpha 1 is validated, we proceed with estimating alpha 2 using the Nelder-Mill method of the linear pattern of estimation of lens distortion correction from single images, being very reliable and robust if initialized with the correct alpha 1. Otherwise, a mismatch is declared. At the end, if a PCE value larger than a set threshold is found, then a match is proclaimed. And to further optimize the computational complexity of the code, we decided to run all these computationally expensive operations like interpolation, resampling, PCE computation and cross-correlation computation, as well as radial correction on a GPU. The results we obtained comparing the OR and max rule against the state-of-the-art methods demonstrate their complementarity, and that further improvement both in terms of true positive rate, ROC curve and computational complexity can be obtained using the PSLR. However, despite the results we obtain with the max OR and PSLR rules, this is just a first step forward in improving the available methods of the state-of-the-art, which anyway still struggles a lot in presence of more complex radial corrections like those applied out camera with Adobe Lightroom. Precisely, the results under the label Lightroom were obtained on images radial corrected out camera with Adobe Lightroom taken with the Canon 1200D and radial corrected for the lens distortion model introduced by the lens mounted on the camera. Instead, the results obtained under Lightroom Star were always images taken with the Canon 1200 but radial corrected for lens distortion models of other lenses, for instance Apple lenses, Huawei, DJI, Tamron or Nikon lenses. Finally, GPU acceleration helps improving the computational complexity of the proposed methods, but we also think that wiser choice in terms of optimization can help to further improve under this aspect. To this purpose, in our future work, we are already focusing in proposing something more efficient, variable and reliable under complex out-camera radial correction. And that's it for today, so let me just get closer to the camera because it's getting pretty dark. I start with the sun again and I end with the night. So that's it for today. I really hope you enjoyed the video, even if the light changed, even if the place is quite empty, will get better. In the future, I think that I adjust some of the lighting and other stuff in post-processing, because now I'm looking at myself in the camera and I think I'm quite bluish. However, as I said, this is it for today. If you are interested to know more, I invite you to check our paper, the reference in the description, and of course our GitHub. And as I said, we are already working on an extension of this work. Actually, we have a paper under revision under review for this work, and I really hope that we are going to be able to present it to you as soon as possible. And as always, if you have a question, the comment section is down below. If you like the video, I invite you to leave a like, and see you in the next one. Bye.